Hello, so today we're going to do Lab 2 Magnetic Field of a Bar Magnet by Mustafa Noor. This is Physics 2212. So, introduction. So, the purpose in this lab, we will measure the distance dependence of the magnetic field due to a small bar magnet and compare our measurements to the predictions made by the equations for the on and off axis magnetic fields derived from the Biot-Savart law. So, that law is shown here. And then we also need to know what the magnetic field of a bar magnet is. And shown on the right, it's K times R to the nth power. And on the bottom is a little picture of how the lab will go. So for the experiment, so first we're going to have to assume that the magnet is a magnetic dipole. The system will obviously be the bar magnet. Surroundings will be none. And the procedure is measure the distance from the magnet to the phone's magnetometer chip based on varying magnitudes of the magnetic field in the x direction or the I hat direction. So for the coding, so first we had to define the dipole B. So first to do that, we needed to define R mag as the magnitude of R, and then R hat as the norm of R. And then after that, we can say that B is equal to P times 1 over R mag to the third power times 3 times the dot of mu and R hat multiplied by R hat minus mu, and that will give us B. And then the code on the bottom left is the codes for the arrows. So we had to define R axis, the B axis, and then that'll give us the arrows in the first direction. And then R axis in the second and B axis in the second will give us a second pair of arrows. And then we can see that B perp is equal to negative 4.20175 e to the minus 5. D is equal to 0.532692. And then B at a 45 degree and at distance D is equal to 1.11189 e to the minus 6. And 3.33356 e to the negative 6, 0. And the magnitude after all that of B is equal to 3.516 e to the minus 6. Questions. When the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. This is obviously true. For the second question, as the magnetometer moves closer to the magnet, the measured x component of the magnetic field decreases. This is false, as we saw it increases. The position of the magnetometer has no effect on the measured x component of the magnetic field. This is also false. And for the last question, as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases, and this is true. Discussion. What if, in the experiment, you oriented your setup so as to compensate for magnetic north? What if you hadn't done that and had instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? How would your results have changed? It would barely have changed our results just a little, but the values would alter slightly, but the magnetic moment would still be pretty easy to find. For the second question, imagine you had two identical magnets. What if you redid the experiment, but instead of using a single magnet, you used two identical magnets stuck together end to end? How would you expect your measurements to differ? So for that, the magnitude of the magnetic field would increase while its direction remains unchanged. This can be compared to a dipole, as when you increase the separation distance, it enhances the electric field, but the direction also stays unchanged. Sources of error. So this is sources of error why the calculated B is different than the computational model of B. So for the first problem could have been outside objects affecting the experiment. Anything laying close to our experiment table or anything under or around it could have affected it, especially if it was magnetic. And then the direction of north was not too exact, as it was a little hard to get it completely exact. And then because my magnet was rounded at the edges, it was hard to calculate its actual length. So there could have been errors in the measured length of the magnet. And that will be all. Thank you.